flashcards last time. Let's just clean some of this up here. All this stuff. Okay. So let's go here. Oh boy, that's 21 cards. Load parameters are oh, actually something more interesting. Literally my first real backend ticket. So, right, like I was doing Kotlin every day. Now I'm writing Kotlin at work. I mostly was just cleaning something up to get the environment set up. So, not like real work, but still something valuable for the team. And now I have a real ticket, like a feature basically. Not a feature, but like a real change. And I have to write a SQL query, and the senior eng that is like helping me kind of onboard and stuff was like, yeah, let's pay attention to the indexes, and then if you run this command, you can see the indexes, and literally like all the indexes popped up, and they're all backed by B trees. So I don't know. I don't need to like really implement this stuff at the moment, but like it kind of all made sense as to what was going on. So it was kind of funny how I was getting worried that like I'm reading through this stuff, but it's like, when is it actually gonna pop up? And even though I don't need to like make something more efficient right now, which I have something to talk about there too. It's like it's there. You know what I mean? Like the thing I'm learning right now is right there, which is pretty cool. And then on top of that, it's kind of cool because there's some real I wouldn't say real yet. There's some performance challenges that the team is facing that I'm probably not equipped to deal with yet. But if they're still there in like a month or two, I think I mean, who knows, maybe it'll even be quicker than that, but like there's just already like real work to be done, and I'm really excited. Really excited about it. So anyway. All right. Okay, so let's come back to the reading in a second. Let's get through these flashcards. Load parameters are a few numbers we can use to describe the load. I can't really remember the exact wording here. It's like a few numbers we use to describe the load, and then if we, I don't know, I can't remember. A few numbers used to describe the load. Oh, that's the whole thing. Example. All right, this was, we'll just say good. A failure is when a system stops servicing users, when it stops doing what it's designed to do. servicing users. Scalability, a system's ability to perform as load parameters increase. Cope with increased load, I'll take that. A fault is when a component of a system deviates from its spec. Latency is how long a request is waiting to be serviced. Impedance mismatch is when the model of, it comes from hardware engineering, but it's when there's a mismatch in the data model and the application model. Storage models, okay. A declarative language describes what you want, but doesn't tell the computer how to get it. The pattern of data, I think that's the important part, the pattern. Yeah. MapReduce is a programming paradigm used to query large distributed, actually I don't know if distributed's the right word, but large data sets. Oh, okay, distributed's part of it, yeah. What is the benefit of declarative query languages like SQL? Because we don't tell the computer how to do it, query engines can be built under the hood, and we can benefit from optimizations that other people implement. Oh. What are the downsides of imperative queries embedded in application code? Imperative queries? So this means we do the joins in code. Business logic is coupled tightly with application logic. More error prone. Slower, right? Because we might have to go to disk multiple times. Error prone, harder to optimize. I'll count that as slower. And tightly couples business logic with data access logic. All right. Normalization is the process of getting rid of duplication in data, reducing duplication. All right. Polyglot persistence, I need to get rid of this card, is using multiple approaches to data storage to fulfill your application's needs. What is the graph data model best suited for? Social networks, recommendations, network topologies. Fine. Compaction is compaction means what does it mean? Okay, so we have a segment file, which is basically an append-only log. We have multiple entries for the same key. Compaction is removing the duplication, or removing the old keys and only keeping the most recent one to reduce the file size. Throwing away the duplicate keys in the log and keeping only most recent, yeah. Tombstones are special logs in append-only logs to mark a key for deletion during the merge and compaction and merge process. An orphan page is in why didn't it change that? In a B tree, an orphan page. Oh, I guess I have this up here. It's when. Oh, if the database crashes while you're making new pages, you lose references. And that means that one of the pages basically has no reference to it. A leaf node has no reference to it. Okay? A write-ahead log is used to make B trees more reliable, and it's an append-only doc that we record transactions for yeah, that let us rebuild the B tree if we need to recover. I didn't even read that. Oops. All right. B trees are a data structure that is not guaranteed, that is always going to be O log n time lookups, and it's has a root page which encompasses the entire range of data that you're storing, but each key can either be a data point or it can be a reference to another page, which would be a leaf node, which contains a subset range of the data. Always balanced. Log in, nice. Fixed page sizes, I forgot that. Have a root page and a leaf page. This was good. An SS table is a sorted string table. I need more. I need more than that. I don't know enough. A log file that is sorted by keys, short for sorted string table, differs from an append-only file. This isn't a helpful flashcard. I don't remember. Log structured. I was thinking log sort, but a mem table is an in-memory data structure to prevent us from going to that we write to first. Once it is a certain size, we create a segment file. Okay. I just realized I think I have. I need to check that. Let me see here. Mm. Mm. All right. I'm getting distracted. All right. Let's lock in. Advantages of LSM trees. I can do that stuff later. A B tree index must write every piece of data at least twice. Once to the write ahead log and once to the tree page itself, and perhaps again as pages are split. There's also overhead from having to write an entire page at a time, even if only a few bytes in that page changed. Some storage engines even write the page twice in order to avoid ending up with a partially updated page in the event of a power failure. At least twice. Once to the write ahead log and once to the tree page itself, and perhaps again as pages are split. Okay, so in write-heavy applications, the performance bottleneck might be the rate at which the database can write to disk. In this case, write amplification has a direct performance cost The more that a storage engine writes to disk, the fewer writes per second it can handle within the available disk bandwidth. Moreover, LSM trees are typically able to sustain higher write throughput than B trees, partly because they sometimes have lower write amplification, although this depends on the storage engine configuration. Okay, so I zoned out. Moreover, LSM trees are typically able to sustain higher write throughput than B trees, LSM trees. Log structure and merge trees are typically able to sustain higher write throughput than B trees, partly because they sometimes have lower write amplification. Okay, which is when one write to database results in multiple writes to disk. Oh, okay, I got it. And partly because they sequentially write compact SS table files rather than having to overwrite several pages in the tree. This difference is particularly important on magnetic hard drives where sequential writes are much faster than random writes. So um, wait, what? Okay, so I don't know if that's actually correct, but I might have just tied that together. Let me ask ChatGPT, what is disk utilization? Let's see. Available disk, okay. Measures how much of the disk's bandwidth and space are effectively used for storing data versus overhead or wasted space. Okay, due to issues like fragmentation, yeah, especially in B trees, or write amplification, where one logical result, yeah, okay, cool, okay. Um, LSM trees can be compressed better and thus often produce smaller files on disk. Some disk space unused due to fragmentation. When a page is split or when a row cannot fit on an existing page, some space in a page remains unused. Oh, I see. Since LSM trees are not page oriented and periodically rewrite SS tables to remove fragmentation, they have lower storage overheads, especially when using leveled compaction. Nice. I'm not gonna lie, bro. LSM trees are pretty dope. On many SSDs, the firmware internally uses a log structured algorithm to turn random writes into sequential reads. On the underlying storage chips, so the impact of the storage engine's write pattern is less pronounced. However, longer write amplification and reduced fragmentation are still advantageous on SSDs representing data more complex, jeez, I can't even talk. More compactly, allows more read and write requests within the available I/O bandwidth. On having trouble focusing. That's right. So okay, now the downside. So I'm not gonna lie, I am having a hard time believing there are any. They sound pretty freaking cool. Okay, a downside of log structured storage is that the compaction process can sometimes interfere with the performance of ongoing reads and writes. Okay. Even though storage engines trying to perform compaction incrementally and without affecting concurrent access, disks have limited resources. So it can easily happen that a request needs to wait while the disk finishes an expensive compaction operation. The impact on throughput and average response time is usually small, but at high percentiles. See describing performance. The response time of queries to log structured storage engines can sometimes be quite high, and B trees can be more predictable. Another issue with compaction arises at high write throughput. The disk's finite write bandwidth needs to be shared between the initial write, logging, and flushing of mtable to disk, and the compaction threads running in the background. When writing to an empty database, the full disk bandwidth can be used for the initial write, but the bigger the database gets, the more disk bandwidth is required for compaction. Interesting. Secondary index. Just zoned out. God. The amount of times I've read the same text over and over. It is also very common to have secondary indexes. In relational databases, you can create several secondary indexes on the same table using create index command. Yeah. Okay. The secondary index can easily be constructed from a key value index. The main difference is that a secondary index, the index values are not necessarily unique. That is, there might be many rows, documents, vertices, under the same index entry. This can be solved in two ways, either by making each value in the index a list of matching rows, identifiers, okay, like a posting list in a full index search, or by making each entry unique by appending a row identifier to it. Either way, both B trees and log structured indexes can be used as, yeah, okay. Let's just try and finish this section. Clustered index. Covering index or index with included columns, which stores some of the table's columns. Interesting. Alright. Right on. 30 seconds left. Alright, we'll call it.